Hey everyone, welcome to yet another video. In this video, we learn about graph data structures. I'm pretty excited because I was a big fan of graph data structures, and by the end of this video, I hope you are a big fan too. So let's just get started. So now let's go on to the graph basics. Now, there are certain terminologies that you need to understand before even going into the graph data structure. Now, first of all, why is graph used? What is it? Graph is a data structure. It is used to store data. But the way we store data inside a graph is much different from what we see in arrays, hash tables, or any other data structure like stacks, queues. So, it is basically used to store data. Let's take a simple example on what kind of data does it store. So the first thing or very simple example that we see in graphs is people and their relationship. So in this, as you can see, we have different people. These nodes that you see here are like people, and the red part that you see that connects with them is like a friendship. So in Facebook, if you see, you are connected with a lot of friends. You have, let's say, 2,000, 4,000 friends. That's how you're connected. So graph data structure in this case can be used to represent all of your friends and their friends and whatnot. So that is one of the examples where graph data structure is used. Now, if you notice, there are these yellow things there, yellow circles. These are like people. But if we have to talk about in graph perspective, these are also called nodes, and the red parts that you see here are called edges. Nodes are also called vertices, but these red ones are called edges. So that is represented now in our picture. These are nodes and these are edges. So those are the two common keywords. Now let's talk about more keywords. Now, as you can see, these nodes, let's say this one and this one, are connected through this edge right here, right? So they are called as adjacent, like an English word, adjacent to each other. That is a keyword that's used quite often. Now, before we move on to another kind of keywords, we need to understand that there are two kinds of graph that we can construct here. Here, you see that the edges do not have a direction, like left to right or right to left. Here, there are no directions. So, these types of graphs are also known as undirected graphs. Whereas there could be another kind of graphs where there is some kind of direction. Let's say for this one, we have a direction from right to left. In this way, let's just change some of these to have some directions. Now this has become a directed graph. Each of the edges have some direction. Now you might be wondering, what is the significance to that? It could be that this person right here has sent a friend request to this person. So basically this guy is following this person. So this arrow can represent the follow direction. So this is how data is stored inside this graph data structure. In the next steps, we'll see how this whole graph data structure that we see here is stored in a matrix or even like a list format. So the first way we store graphs is called as adjacency matrix. This might seem complicated, so let's take a look at the left part. Here I have named all of these vertices as 0, 1, 2, 3 and 4, and it's the same graph that we saw earlier. Now, how do we store this visual representation of the graph into a matrix? We basically ask this question, are 0 and 1 connected? If so, we just fill in that, okay, 0 is connected with 1. So in this whole matrix that you see, we see this entry, 0 is connected with 1 or not here. In this case, it is connected, and that is why we have filled 1 here. But what about the case between 0 and a 2? They are not connected, so that's why for 0 and 2, we have an entry of 0. Similarly, we fill all of these entries in this matrix, such as for 1, 1 is connected to 0, 2, 3 and 4. So for 1, it's connected with 0, 2, 3 and 4. So all of those are 1 in this matrix. So that is how we store the whole graph in a matrix format. Now if you notice, we have these zeros in the diagonal here. Why is that so? Because we say it's like convention saying that 0 is not connected to itself. If this was the case, if we had a edge like this, then we would have filled this one as a 1. But since it's not, we just get rid of that. Now, if you notice a small detail in this adjacency matrix, it's a symmetric matrix. If you see, the whole matrix is symmetric around this line, diagonal line. So 1 1 0 0 1 1 1 1 0 0. The whole matrix is symmetric. That makes sense too, right? If we say 1 is connected to 2, then we can also say that 2 is connected with 1. And that is the same case with 1 3 3 4 and 1 4. If 1 is connected with 3, 3 is also connected with 1. And that is the reason why this whole matrix that we see here is symmetric. So now we know how it is represented in a matrix format. Now let's look at the code part. In here, you can see that we have initialized n equals 5. Then we have a matrix. And for each of the matrix entry, example, adjacency matrix 0, 1, we set that value to 1. We set that value to 1 for 1, 0. Similarly for all of the others. Fairly simple, right? Now, I want you to notice what is the advantage of storing the graph in this fashion and what are the disadvantages. Pause this video here and try to think about it. Okay, now I'll tell you what are the advantages and what are the disadvantages of this method. The advantage is pretty straightforward. If we want to check if there is an edge between 1 and 2, we can simply just call adjacency matrix 1 and 2 and we can just check for that entry inside this. It says 1. Okay, they are connected. So the lookup for checking if there is an edge between 1 and 2 or any two vertices is pretty quick. It's like O1 time complexity. So that is for the advantage part. Now comes on to the disadvantage of this method. The main advantage in this method is that it is storing a lot of redundant values. If you see, we noted that, okay, this is a symmetric matrix and this part right here can tell us all the information. We don't need the lower half. Why so? Because if we say that 0 and 1 are connected, then 1 and 0 is already connected. So why to fill in all of these data? And many a times these graphs are not much connected. Now what do I mean by not much connected? Let's say that these edges are not much connected, something like this. In this case, we'll still be storing all of that information inside this matrix here, and most of the entries would be 0. So most of the storage is wasted in storing these zeros, and that is the main disadvantage. To make you understand the main problem here, let's say we go to the scale of Facebook, where they have, let's say, 1 million, I'm taking a smaller number here, but let's say 1 million people on the platform. So for 1 million people, we'll need to have this 1 million into 1 million matrix, which is a huge number. And most of the people aren't connected to. So most of the entries in that matrix would be 0. And that is why in most cases, we do not use adjacency matrix. We use something called as adjacency list. So let's take a look at that now. So this is how an adjacency list looks like. As you can see, we have for each of the vertices, we have a list. So let's say for the 0th vertex, we have a list attached to it, which says, okay, 0 is connected to 1 only. This here, as you can see, is a list. Similarly, we'll have list for each of the vertices. So let's say for second is connected to 1 and 4. And that is what we see here in this list. So it's a much more efficient model here because we are not storing zeros saying that this isn't connected. We are only storing the presence of edges, saying that vertex A is only connected to B and C. Now let's look at how we write code for this one. So similarly, as we saw earlier, we indicate n equals 5. We indicate list of integers called as adjacency L. This here, as you can see, is a list of list. And as you can see, for adjacency list 0, this particular thing is a list. Inside of that, we are adding 1 here. Similarly, for adjacency list 1, indicating here, we are adding 4 entries here, 0, 2, 3, and 4. Here we have all of those things. So this is how it's represented. Much efficient, as you can see. We don't need to store 0, 0, zeros for the vertices that aren't connected. Now we know how to store graphs, but what are some common queries that are asked in this graph data structure? Well, one could be, tell me if this graph has X node in it. Let's say somebody is searching in this graph, searching for, let's say, 4th node. Or maybe find me all the nodes with some XYZ condition. Let's say, which of these nodes are having the values as even numbers? There could be many such conditions. Or maybe, is there a path between 0 and 2 or 1 and 4? There could be multiple such queries. If you notice, there's one thing in common there. We are trying to traverse this whole graph and compute these results here. That is what it is, right? So that is a common operation. So if we have to collect all of those queries, we would just say that we need to find a way to do traversals in this graph. Now, there are two kinds of traversals that are very, very common. There could be more, but there are two very common ones. The first one is depth first search, and the second one is breadth first search. So let's look into that. So this is the overall idea of what depth first search is. So let's say we start the traversal at the 0th node here. We mark this as visited. Okay, we have visited the 0th node. Now, let's move on to one of its neighbor. In this case, let's move on to this direction and say we have visited the first node. Now we'll move on to the neighbor for this first node here. So now there are two neighbors here, 2 and 3 here. But we'll move on to one of them. Let's say we move on to the second one. And we mark this one as visited 2. Now, we do not have any neighbors to 2. So we'll move back to the first one. Now we'll say that 1 had another neighbor called as 3. So we'll move in that direction and call it visited. Now if you see, all of the nodes are visited and we are done now. So what did we do basically? We went into the depth first. We went from 0 to 1 and then 2, basically going until we have found a particular node where there are no neighbors. Once we are done with that, we come back and see what are the neighbors for the first one. In this case, it was 3. So we went into 3 and we went until that point where 3 had no neighbors which are not visited. It might seem quite complicated, but let me simplify this now. So let's run through this example here. So we'll start off with 0. We'll mark this as visited here by changing it to 1. Now, the next step, we'll move on to DFS. The DFS 0 would call DFS 1. And then that will be marked as visited. So I'll just remove this and mark it as 1. Now, the DFS 1 had two options, either go into or either go to the third one. We go on to the second one and then mark it as visited. So I'll mark it as visited. Now if you see, 2 doesn't have any neighbors that are not visited. So that is why we can't go anywhere from here. That is why we come back to the first node and then see what are the other neighbors. In this case, 1 had neighbor for 3 here. So that is why we went on to 3 and marked that as visited. So basically calling DFS 3. But did you notice one particular thing here? We never even touched this part of the graph. Why so? Because we started off from 0th one and we moved on to all of the connected ones from the 0th node. Since 4 and 5 aren't connected, we couldn't do a DFS to that. So that is why what we do in a depth first search is we try to do a DFS on all of the vertices. We start off by doing a DFS from 0 and then from 1, then from 2, then from 3, then from 4, then from 5. Now there could be many repetitions as you can see. Since we are doing a DFS from 0, we have already covered 0, 1, 2 and 3. So we do not need to do DFS from 1, 2 and 3. So that is what we'll see in the code part, where we'll have a check on each of the vertices. if they aren't visited, then only start a DFS from them. If this is very complicated, let's look at the code part, run through a small example and understand this bit too. So this is how the code looks like. We have the input as adjacency list here, a visited array, which looks like this in the beginning. Then we have the start node. From where do we want to start the depth first search? So in this case, let's say the start node is 0. So we'll print that out. Let's say we print 0, then we'll mark that as visited. We'll remove that and mark that as visited. Then this particular loop is for looking at all of the neighbors for 0th node, and for all of the neighbors for 0, we'll look at all of the ones that aren't visited. So that is being checked here. We'll check, okay, which of the neighbors have the visited the value as 0. So in this case, both of the neighbors 1 and 3 have the value as 0. Here you can see that. So let's say we start off with the first one. We'll say, okay, if visited 1 equals 0, in this case that's true, we'll call for a DFS on that particular node. So that is why we see DFS 0 is calling DFS 1 here. Now, once we are at DFS 1 here, we'll print out one value. So this is 1 here. And then we'll mark the visited 1 as 1. So let me mark this as 1. And let's just check this. Now we'll look at all of the neighbors for 1 which aren't visited. So for 1, there are 2 neighbors, 2 and 3, which aren't visited. So for this loop here, we'll look at visited 2 equals 0 or not. In this case, that's true. So we'll call DFS 2. That's what we have done here. And let's just change this to DFS 2. We'll print that out. That is 0, 1, 2. And then mark that as 1. So that is done. So this is visited now. Now we'll look at all of the neighbors for 2 that aren't visited. Since 2 has only one neighbor, which is 1, which is already visited, we won't go anywhere in this loop here. Now since DFS 2 is done, we'll backtrack to DFS 1. Now we were in this loop and we are done with the second node. We'll look at another neighbor for 1, which is 3, and then check if visited 3 equals 0. In this case, it is true. So we'll mark this as 1. Now we come back to this loop again. Now when we were in this loop for DFS 1, we had another neighbor, which is the third one. So we'll check, okay, visited 3 equals 0 or not. In this case, it's 0. So we'll call for the DFS 3. So that's what we are doing here. So let's just change this value to 3. We'll print that out. So in this case, we'll print 3 and mark this as 1. Now we'll look at all of the neighbors for 3 which aren't visited. In this case, both of 0 and 1 are visited. So we won't do anything here and we'll simply backtrack to DFS 1. Now for first node, it doesn't have any neighbor that aren't visited. So this call is done now. Now we'll backtrack to DFS 0. Again, for 0, in this loop, we do not have anything to do because all of the nodes that are neighboring are already visited. Now we are done with visiting all of the nodes inside this part of graph. But what about this one? We haven't visited 4 or 5. So as I hinted early on, we'll do a DFS on all of these nodes individually, and if they aren't visited, then only we'll initiate this DFS call. Seems confusing? Let me write down the code and it will be much more simpler. Now this part that we have added here will complete the complete DFS. Now what do I mean by that? As we saw previously, we were able to do a DFS on this particular part successfully because we started from 0th node. But we never visited 4 or 5. So that is what we are trying to achieve. We are trying to traverse all of the nodes. If you look closely in this graph_DFS method, we are first of all initializing visited as all zeros. We'll basically have all zeros here. So we'll have all zeros in the visited here. And then we'll run a loop from 0 to n, basically running for all of the vertices, and basically ask this question: is the first vertex visited or not? If it's not visited, then only run this DFS code. Now, if we had to simulate it, let's say if we would have started off from the 0th node here, we would have visited 0, 1, 2, and 3, basically this part of graph. So when this loop starts here, for this particular part, when DFS 0 was called, all of these 0, 1, 2, 3 would be marked as 1. So let me change that. Now, when we call for DFS 1, it would simply check for this condition right here and say, okay, visited 1 is not equal to 0, so don't run DFS on it. So it will skip this. Similarly, it will skip for 2, similarly, it will skip for 3. But for 4, it won't skip it because the entry there is 0. So this condition would hold true now. Now, a DFS would be called from the 4th vertex, and when we do a DFS from 4, 5 will also be marked as visited. So let me change this to 1 and 1. So now we had traversed the whole graph here. So let me clean this up first. So now if you had to write code for the depth first search, it would include both of these parts because that would ensure that we are covering all of the vertices in that graph. And this is the code that you need to remember. Both of these, graph DFS and DFS, both of them, you need to remember for your interview purposes. Now, since we are already here, let's now talk about the time complexity and the space complexity for depth first search. Now, if you notice, in the whole DFS process, we are visiting each of the node only once, and we are checking each of these edges at least once when we are doing this step here. We're checking for the neighbors for each of the nodes. So that is why the time complexity comes out to be O of V plus E, where V is the number of nodes and E is the number of edges. Now, talking about the space complexity, the auxiliary space complexity for this is O of V. Well, some might argue that we have taken space here where we are having the adjacency list and it should be O of V plus 1. But we are talking about extra space that we are using. For the DFS part, we only had a visited array, this part that we added here. So that is why the space complexity should be O of V. That is the number of vertices. And that completes the whole depth first search. Now let's move on to the breadth first search. Now let's talk about breadth first search. Now as the name suggests, breadth first search will do search in such a fashion or traverse in such a fashion where we are going breadth first. That is, we'll look at our nearest neighbors first and then we'll expand our breadth and look for more neighbors. Now that might seem confusing. Let's take an example to understand this better. Let's start off from 0. Let's say we visited the 0th node here. We mark it as visited and print it out. Now we'll look for all of the neighbors to this one, which is 1, 2, 3, and 4. So we'll mark them as visited, 1, 2, 3, and 4. We'll just print it out, 1, 2, 3, and 4. And now you see we have gone to a breadth of 1. That is 1 nearest neighbor to 0. Now let's expand this breadth to 2. Now 0 had one of the neighbors as 1. Now 1 has its neighbor as 6 and 6 has a distance of 2 from 0. So we'll be marking that as visited. Similarly, 7 is also at a distance of 2 and is a neighbor for 3. Similarly, 5 is at a distance of 2 and is a neighbor of 2. So we'll visit that too. So we'll have 6, 7, and 5. So that is how things happen in breadth first search. Our approach here is to visit our nearest neighbor first and then look for the neighbors from the new nodes, that is 1, 3, 2, and 4. And we'll keep on expanding this, basically expanding to let's say a distance of 1, distance of 2, and let's say distance of 3. Maybe it had a neighbor of, let's say, a node 8. So we'll keep on expanding this breadth. Now we can move on to the implementation part. Okay, now let's look at the implementation. We have added 2 bits here. One is an array here, as you can see. It's a visited array which keeps track of which of the nodes are visited or not. And the second thing that we'll use here is a queue here. This is a queue which will be useful in doing the implementation for BFS. Let's understand this using an example. Let's start off with the 0th node. As the step 1 suggests, we'll add the start node to the queue and mark it as visited. So I'll add 0 to this queue and mark it as visited here. Now, what is the next step? We'll add all our unvisited neighbors to the queue. Well, basically what we are doing early on, we were looking for all of the neighbors around the starting node. And once we are done with adding the level 1 of neighbors, we'll add level 2 of neighbors. In this case, level 1 is 1 and 3 and level 2 is 2. So we'll keep on doing that. Let's just move forward with our algorithm here. So we'll add all our unvisited nodes to this queue and then mark both of them as visited. So we'll do that. But we also need to pop this out. So I'll just pop it out because we are done with the 0th node. Now we'll repeat this process. We'll pop things out of this queue and then look for all of the unvisited neighbors, mark them as visited and add them to the queue. So if we pop out 1, we'll look for one of its neighbor, which is 2. So we'll add that to the queue. And since it's a queue, 2 goes behind 3. And once we are done adding all our unvisited neighbors to the queue, which in this case is only 2, we also need to mark them as visited. So let me mark that as visited. Now we'll pop out 3 and look for all of the unvisited neighbors to 3. In this case, there is 1 and 0, but both of them are visited. So we don't need to follow any of these 2 steps here. So we'll simply pop this out. Now let's move on to 2. We'll pop it out. Now when we are popping it out, we'll look for all of the unvisited neighbors and add it to the queue. So let me do that here. I'll add 4 here and also mark it as visited. So I'll mark 4 as visited here. Again, we'll repeat this process. We'll pop 4 out and look for all of the unvisited neighbors. For 4, there are none. We had 2, but it's visited. So we don't need to follow any of these 2 steps here. So with that, we are done with the BFS for this part of the graph. But what about this part here, 5 and 6? Those are untouched, where it's very similar to the DFS part, where we had to start a BFS from each of these nodes. So let's take a look at that next. So this is what I'm talking about here. When we are doing a graph BFS on this whole graph here, that is graph BFS here, we'll have to do BFS starting from 0, starting from 1, starting from 2, 3, 4, 5 and 6. But we can't keep on doing BFS for all of these nodes because once we are done with doing BFS from 0, we have already marked all of these as visited. So our efforts would be wasted here. We'll be repeating things. So we'll have a condition there. If that node is not visited, then only call BFS for that. So let's say we'll call for 0. All of these get marked as visited. Then we don't need to call BFS on 1, 2, 3 and 4. But when we come to 5, it sees that it's not visited yet. So it will call a BFS on 5. But when it does a BFS on 5, 5 and 6, both of them get marked as visited. Now, when the loop goes to BFS for 6, it won't do a BFS on 6 because it's already visited. So this is how we do a BFS on the whole graph. We'll basically have to loop from 0 to 6, and for each of the nodes, we'll have to call BFS. But since some of them are already visited, we'll basically skip these. So that is the whole idea. Now let's take a look at the code for the BFS. Now let's learn about BFS code. So this is how it looks like. It might seem a little bit complicated, but stay with me for the whole time and you'll understand the whole concept very easily. Let's say this is the BFS algorithm. It takes in the adjacency list that we have seen. It also takes the visited array, which is initialized to all zeros, and we have a start node from where we start. So the first step is when we do some initialization for a queue. So this initializes the queue. Next, we add the starting node to the queue. So let's say in this case, we start off with the 0th node. So we'll add this to this queue here and mark it as 1 that we have visited it. Now, this loop starts. And what does this loop consist of? We'll continuously do these steps inside this loop. We'll pop the element out. Let's say this part. We'll pop the element out, and for all of its neighbors, we'll add all the unvisited neighbors inside this queue right here. So that is the whole concept. And while we are doing that, we'll mark them as visited. Seem confusing? Let me just go through this example now. So let's say we start off with this loop here. The current equals q.pop. So that is the 0th element. So let me just pop this out. So this has popped out now. We'll print it out. So let me just print it out as 0. Now this loop basically says that we are looking at all of the neighbors for this node here. So what are the neighbors for this node? Which is 1 and 3. So for both of these, 1 and 3, we'll ask this question, is visited I equals 0 or not? So in this case, both 1 and 3 have 0 in here, basically saying that they are unvisited. So for them, we'll simply add it to the queue. So let me add it 1 and 3. And while we are doing it, we also have to mark them as visited. So let me go ahead and mark them as visited. Now let's go back to this part of the loop again. Q is not empty and the current element is 1, which is at the top. We'll pop it out. So 1 comes out and we'll print it out. So this comes here 0, 1. And now for all of the unvisited neighbors for 1, we'll need to add them to the queue and mark them as visited. So for 1, we have, let me mark this as visited, this one too. So for all of the unvisited neighbors for 1, in this case we see that it has 0, 3 and 2 as neighbors, but only 2 is the one which is unvisited. So for that, we'll add it to the queue and we have to add it here. And while we are doing that, we'll have to mark it as 1 and basically marking it as visited. So let me just mark this as 1. Now we are done with 1. So let me just get rid of this. Now again we are at this part of the loop. Now we are again at the start of this loop. We'll pop this element out and we'll print it out. Let's say 3. And for all of the 3's neighbors which are unvisited, we'll have to add them to the queue. In this case, all of its neighbors 1 and 0 are visited. So we can't add anything to the queue. So we are done with 3. Now we are back at the start of the loop. We'll ask this question again. Is the queue empty? Well, not empty. We'll pop it out and print it out. And for all of the 2's neighbors which are unvisited, where basically visited I equals 0. In this case, 2's neighbors are 1 and 4. And only 4 has the entry as 0 in the visited array. Basically, it's unvisited. So we'll mark that as visited here and add it into the queue. That's what these steps say here. Okay, now we are back at this loop here. So we'll pop this out. We'll print it out. And for all of its neighbors which are unvisited, we'll need to add them to the queue and mark them as visited. Now, 4 has a neighbor as 2, which is already marked as visited, so we don't need to do anything here. So we are done. So we just printed 0, 1, 3, 2, 4. But wait, we were unable to reach all of the nodes in this graph. We never visited 5 and 6 here. So next we'll see updates to the BFS in which we'll cover all of these nodes. So this is the small change that we need to do. This is the code part that we just saw, which will run a BFS starting from a start node, but we'll have to run it for all of the nodes individually. So that is what we'll do in this code here. So the graph BFS takes input as adjacency list and n as the number of nodes. We'll first initialize the visited array here, and then we'll run BFS for all of the nodes starting from 0 to n. But wait, why is there a condition for visited I equals 0? Let me show you. So let's say we start off this BFS from 0th node. So we'll mark this as visited 1, 3, 2 and 4 as visited. And so let me just change these values to 1. So now let's say we have to run this loop for 0 to n. For 0 we just ran it and marked all of the things as visited here. When it comes to 1, it will just check, okay, visited I is not equals to 0. It's 1 here. So it won't run BFS for BFS 1. Similarly, when it goes to 2, it won't run it for BFS 2. It goes until 4, but when it reaches 5, it will need to run BFS for it. That is because visited 5 equals 0, which satisfies this condition right here. So in this case, BFS 5 will be ran, and when it is run, it will mark it as visited for 5 and 6. And that is why we have this code part here. If you combine both of these parts, that is the code for complete BFS. And I want you to remember this whole code as a template because it will be used in all of your interviews. This is a very common pattern and we'll see multiple sub patterns coming out of this BFS. So my recommendation would be to just remember this. Now let's talk about time and space complexity. If you take a look at this part, you can observe that we are looking at each of these nodes at least once. We are adding them to the queue and then looking at its neighbors. So we are at least looking at these nodes at least once. Now if you look at this part, we are looking at all of its neighbors at least once. By neighbors, I mean edges. So we look at each of these edges or each of its neighbors at least once. So that is why we say that the time complexity is O of v plus 1. And space complexity is pretty simple to understand. We are only using one visited array here. So the extra space that we use was of order of v, which is nodes or vertices.